The atmospheric scientist pulled up the comparison chart at the beginning of the Tuesday morning briefing and did not say anything for approximately 8 seconds. The people in the room, her colleagues from the Weather Research Division of a major Pacific meteorological agency, were accustomed to her opening briefings with data rather than with words. But 8 seconds of silence while she looked at her own chart was long enough to shift the quality of the attention in the room. When she finally spoke, she did not begin with the usual summary of the previous week's activity or with the overview of the current large-scale circulation pattern. She began by asking a question. She asked whether anyone in the room had seen a comparison chart like this before. The chart was a side-by-side display of 2 typhoon season timelines. The left panel showed the composite climatological average of Western Pacific typhoon activity for the current calendar period, derived from 6 decades of storm track and intensity data, showing the typical distribution of storm formations, the normal pattern of peak intensity events, the standard envelope of where and when the major typhoons of the Western Pacific Basin tend to occur during this period of the season. The right panel showed the current season. The number of storms in the current panel was not dramatically higher than the climatological average. The locations of formation were not dramatically different. What was different, and what the silence in the room was about, was the intensity distribution. The storms in the current season panel were, as a population, stronger than the storms in the climatological average panel. Not all of them, not dramatically in the case of each individual storm, but the distribution was shifted, systematically and coherently, toward higher intensities across the full range of the season's active systems. The storms that had been tropical depressions in the climatological average were tropical storms in the current season. The storms that had been moderate typhoons in the average were strong typhoons in the current season. The storms that had been strong typhoons in the average were super typhoons in the current season. The distribution was shifted, and the shift was visible across the full range, not in one anomalous event that could be attributed to unusual local conditions. She asked again whether anyone had seen a comparison chart like this before. One of her senior colleagues said that he had not seen a chart exactly like this, but that he had seen forecasts suggesting that something like this might eventually happen. Papers from the research community going back several years that had projected how the distribution of typhoon intensities would shift. As the Western Pacific Ocean warmed and the conditions for extreme intensification became more prevalent, he said that the papers had been describing a gradual process that was expected to unfold over decades. He said that looking at the current season chart, he was starting to wonder whether gradual was the right word for what was happening. No one else in the room said anything for another few seconds. Then the briefing began in earnest, with the meteorological precision and the operational focus that the institution demanded, but with an undercurrent of something that was harder to name than concern, and that shaped the way everyone in the room approached the data for the rest of that day. The Western Pacific Typhoon Basin is the most active tropical cyclone basin on Earth. It generates more named storms, more typhoons, more major typhoons, and more super typhoons than any other basin in any given year. Driven by the extraordinary concentration of warm ocean water in the Pacific warm pool and the broad equatorial expanse of ocean over which organized tropical convection can develop and intensify before encountering the land masses and the cooler waters that eventually limit the life cycle of individual storms. The basin has produced some of the most powerful tropical cyclones ever recorded by human instruments, including Typhoon Tip in 1979, whose central pressure of 870 millibars remains the lowest reliably measured for any tropical cyclone in history, and Typhoon Haiyan in 2013, whose maximum sustained winds at landfall in the Philippines were among the highest ever observed for a landfalling tropical cyclone. The Western Pacific is where the atmosphere demonstrates most clearly what it is capable of when the conditions are right. The science of how typhoon intensity is distributed across a season, of what determines the frequency of extreme events versus moderate ones, is one that has been developing rapidly in parallel with the broader science of how a warming climate is changing the statistics of tropical cyclone activity globally. The theoretical framework that guides this research is well established. The potential intensity of a tropical cyclone, the theoretical maximum intensity that a storm can achieve in a given set of thermodynamic conditions, scales with the temperature of the ocean surface and the temperature of the upper atmosphere in a way that has been understood since the seminal work of Kerry Emanuel and colleagues in the 1980s and 1990s. As the ocean surface warms, the potential intensity ceiling rises. As the ocean surface has been warming, the ceiling has been rising, and the most intense storms in any given season have been approaching and sometimes reaching levels of intensity that were previously rare or unprecedented. The shift in the distribution of typhoon intensities that the comparison chart showed is consistent with this theoretical expectation, but its magnitude and its clarity in a single season were notable enough to prompt the question that the atmospheric scientist asked twice during the Tuesday morning briefing. The theoretical expectation had been framed primarily in terms of multi-decadal trends. the slow statistical emergence of a higher intensity distribution from the noise of interannual variability over periods of decades. What the current season's data was suggesting, at least in the preliminary analysis available at the time of the briefing, was that the shift in the distribution was large enough to be visible within the statistics of a single season, a possibility that the theoretical framework allowed, but that the observational record had not clearly demonstrated before. The specific mechanisms by which the current typhoon season's unusual intensity distribution is being produced are not reducible to a single cause, and the meteorological community that is examining the season in real time is careful about attributing any single storm's behavior to any single factor. Tropical cyclone intensity is a complex function of many environmental variables, including sea surface temperature, ocean heat content, upper-level wind shear, atmospheric moisture, and the large-scale circulation pattern that determines the environment through which a developing storm moves. Each of these factors can vary independently, and their combined effect on intensity can be constructive or destructive, depending on whether their variations are aligned or opposed. What the current season appears to be exhibiting is an unusual alignment of multiple factors in the direction of supporting higher intensities. An alignment that is not entirely random, but that reflects specific features of the current atmospheric and oceanic state that are themselves the products of the longer-term trajectory of the climate system. The sea surface temperatures across the western Pacific are elevated above the long-term climatological average by margins that, while not unprecedented in any specific location, are consistently elevated across the full breadth of the Typhoon basin in a way that has not been observed in previous seasons. The warmth is not concentrated in a single anomalous warm pool or in the region of the basin most frequently traversed by typhoon tracks. It is distributed, covering the full geographic range within which typhoons develop and intensify during the season, providing elevated thermodynamic support throughout the typical development region, rather than in specific windows that individual storms must be fortunate enough to encounter. The ocean heat content, which is the subsurface thermal energy that determines how effectively the self-limiting upwelling cooling mechanism operates, and which matters more for extreme intensification than the sea surface temperature alone, has been elevated in the western Pacific in ways that the Argo Float network has been documenting throughout the year. The anomaly is not uniform across the basin, but it is present in a broad enough region to have affected the intensification of multiple storms during the current season, each of which has encountered deep, warm water that has allowed it to intensify more rapidly and to greater intensity than it might have achieved in a season with more typical subsurface thermal conditions. The upper-level wind shear, which is the environmental variable that the models identify most consistently as a limiting factor for typhoon intensification in the western Pacific, has been generally lower than average across much of the basin during the current season, a feature of the current large-scale circulation pattern that reflects both the specific ENSO state and the broader pattern of atmospheric circulation that has characterized this period. Low wind shear is not a guarantee of extreme intensification, but it is a necessary precondition, and its persistent presence across the development region of the basin during a period when the oceanic conditions are also unusually favorable for intensification is part of what has enabled the unusual intensity distribution that the season is producing. The combination of these factors, elevated sea surface temperature, elevated ocean heat content, and reduced wind shear, occurring simultaneously across a large portion of the Typhoon basin, represents a convergence of favorable conditions for extreme intensification that is unusual in the climatological record. It is not impossible to explain within the framework of natural interannual variability, since each factor individually has been at comparable levels in past seasons. What makes the current situation unusual is the simultaneous favorable alignment across multiple factors over a sustained period, a combination that the historical record suggests occurs rarely, and that the theoretical framework predicts should become less rare as the climate warms and the oceanic baseline shifts toward conditions that are more consistently supportive of extreme intensification. The practical consequences of the unusual intensity distribution for the communities and the infrastructure in the Western Pacific Typhoon Belt have been accumulating throughout the current season, with each storm that has reached or exceeded the major typhoon threshold adding to a ledger of damage and disruption that is beginning to tell a story about what a systemically intensified typhoon season means for the societies that are in its path. The Western Pacific Rim encompasses some of the most densely populated coastlines on Earth. The Philippines, with a population of more than 110 million people distributed across an archipelago that sits squarely in the primary typhoon track corridor, is among the most typhoon-exposed countries in the world, experiencing an average of 20 typhoons per year, of which approximately 8 to 9 make direct landfall. The country has developed significant typhoon preparedness infrastructure over decades of experience with destructive landfalls, including early warning systems, evacuation protocols, and a network of evacuation centers that can shelter large numbers of people during the passage of major storms. This infrastructure has saved lives in major events and reflects the institutional learning that comes from repeated exposure to typhoon disasters. But the infrastructure was designed and calibrated around the historical distribution of typhoon intensities, and the current season's distribution is shifted toward the higher end of that historical range. The evacuation centers that provide shelter for coastal communities during typhoon landfalls are designed to withstand specific wind speed thresholds derived from the building codes and the historical frequency of those thresholds being exceeded. A systematic shift in the intensity distribution toward higher values means that a higher fraction of landfalling storms will reach or exceed the design wind speeds of the evacuation centers than historical experience would suggest, a possibility that the Philippine Atmospheric, Geophysical, and Astronomical Services Administration and the National Disaster Risk Reduction and Management Council are working to incorporate into their operational preparedness frameworks. Japan, whose typhoon exposure is concentrated in the summer and autumn months when the western Pacific tracts that bring storms northward toward the Japanese islands are most active, has, among the most sophisticated typhoon preparedness infrastructure in the world, built over decades of national investment in disaster risk reduction. The Japan Meteorological Agency's typhoon forecasting capability is recognized globally as among the best, and the country's infrastructure for communicating storm warnings and coordinating evacuation and preparedness activities is extensive and well practiced. Japan's vulnerability to the current season's unusual intensity distribution is therefore different in character from the Philippines' vulnerability. The concern is not primarily about whether the warning and evacuation systems can function under the current conditions, but about whether the physical infrastructure, the seawalls, the flood control systems, the building stock in coastal areas is designed to the level of protection appropriate for storm intensity distribution that is higher than the distribution used to calibrate the design standards. The specific design standard issue has been discussed in the Japanese engineering and hazard planning community for years in the context of the long-term trend toward more intense typhoons in the western Pacific and the implications of that trend for the performance of infrastructure designed to past historical standards. The current season is sharpening that discussion by providing concrete evidence that the distribution shift, which the design standards discussion has been conducted in terms of theoretical projections and long-term trends, is now visible in the statistics of a single season. The research community that is attempting to understand what the current season means in the broader context of Western Pacific typhoon climatology is working with several interacting timescales and several interacting physical mechanisms, and the difficulty of separating the natural interannual variability of the basin from the longer-term trend that the theoretical framework predicts is one of the central scientific challenges of the analysis. The interannual variability of typhoon intensity in the Western Pacific is large, driven primarily by the ENSO cycle, but also by the Pacific decadal oscillation and other modes of low-frequency climate variability that modulate the sea surface temperature and the atmospheric circulation of the basin on timescales of years to decades. During El Niño years, when the central and eastern Pacific are anomalously warm, the typhoon track in the western Pacific tends to shift eastward and poleward, and the storms that develop tend to spend more time over the warm waters of the open Pacific before encountering cooler water or land, which tends to favor higher peak intensities. During La Nina years, when the western Pacific is anomalously warm, storms tend to form further west and to make landfall earlier, spending less time over the open ocean and sometimes not reaching their maximum potential intensity before landfall. Neither of these generalizations applies cleanly to the current season, whose ENSO state has been transitioning from La Nina toward neutral during the period of the unusual activity, producing a mixed atmospheric and oceanic background that the simple ENSO-typhoon intensity relationship does not cleanly predict. The Pacific decadal oscillation, a longer timescale mode of variability associated with the temperature pattern of the North Pacific Ocean, is in a phase that is broadly consistent with conditions that have historically been associated with more active and more intense Western Pacific typhoon seasons, adding a background favorable for intensity that compounds the ENSO signal. The combination of the transitioning ENSO state, the favorable PDO phase, and the elevated oceanic baseline is producing a compound favorable environment whose statistical frequency in the historical record is low, reflecting the rarity with which all of these factors have aligned in the favorable direction simultaneously during the period of reliable observation. The difficulty in attributing the unusual current season to any single factor reflects the genuine multi-factor character of the phenomenon. Typhoon intensity is not determined by any single environmental variable, and the unusual intensity distribution of the current season is the product of an unusual alignment of multiple variables. The long-term climate change signal, the elevation of the oceanic baseline that the greenhouse effect is producing, is one of those variables, and it is the one that the theoretical framework predicts will become progressively more important in determining the statistics of the intensity distribution over the coming decades. But in any specific season, the natural variability factors, the ENSO state, the PDO phase, the specific pattern of the monsoon circulation, are also significant, and disentangling their contributions from the greenhouse gas signal is a challenge that the attribution science community is working on, but that has not yet reached a definitive answer for the current situation. What the science does support is the statement that the current season's unusual intensity distribution is consistent with both the expectations from the long-term climate change signal and with a combination of favorable natural variability factors, and that distinguishing between these two contributing causes with confidence requires more analysis than is currently available. This is an honest and carefully calibrated scientific statement that acknowledges the genuine complexity of the attribution problem, while being clear about what the evidence supports and what it does not. The typhoon forecasting community is facing a specific operational challenge in the current season that is distinct from the scientific challenge of understanding its causes. The operational challenge is that the models being used to forecast typhoon intensity were calibrated and validated against the historical intensity distribution of the Western Pacific. And if the current season's distribution is genuinely shifted from that historical distribution, the models may be systematically biased toward underforecasting the intensity of storms that develop in the current unusual environment. This is the same issue that arose in the context of specific individual storms earlier in the season, but it extends to the broader question of whether the operational forecasting framework is adequately representing the current state of the basin. The evidence that the models may be systematically underforecasting intensity in the current season comes from the season-to-date verification statistics, which compare the operational model forecasts with the actual observed intensities of the storms that have occurred. In a well-calibrated forecasting system, the verification statistics for any given season should show errors that are randomly distributed around zero, with storms as likely to be stronger than forecast as weaker, and with the magnitude of the errors consistent with the historical spread of forecast errors. The current season's verification statistics show a systematic pattern of the storms exceeding the model forecasts in the direction of greater intensity, with the magnitude of the positive errors larger on average than the historical distribution of forecast errors would predict. This pattern is consistent with the hypothesis that the models are systematically underforecasting intensity because they are not fully representing the unusual oceanic and atmospheric conditions of the current season. The operational implications of this potential systematic bias are significant. If the models are underforecasting intensity, the watches and warnings issued for typhoons approaching coastal areas may be based on intensity forecasts that are lower than the actual intensities that will be experienced, leaving communities less prepared for the storms that actually arrive than the official warnings suggest they should be. The forecasters at the operational agencies are aware of this issue and are applying subjective adjustments to the model guidance to account for the perceived bias. But the adjustments are themselves uncertain because they depend on the judgment of the forecasters about how large the bias is and how it should be corrected in specific situations. The methodology for making these adjustments and the broader question of how operational forecasters should account for systematic model biases that are not yet well characterized is an active area of discussion within the forecasting community. The tension between the need to provide warnings based on the best available model guidance and the awareness that the model guidance may be systematically biased in a specific direction is one that does not have a clean resolution. And the current season is sharpening the practical stakes of the discussion in ways that the more theoretical treatments of the problem have not. The historical context for unusual typhoon seasons is a dimension of the current scientific discussion that is important for calibrating the level of concern that the season warrants. The Western Pacific has produced extraordinary seasons before, seasons whose intensity statistics were significantly above the climatological average, and that were associated with specific combinations of favorable oceanic and atmospheric conditions. The 1997 typhoon season, occurring during the strongest El Niño event of the 20th century, produced an above-average number of intense typhoons and included several storms that reached exceptional peak intensities. The 2013 season produced Typhoon Haiyan, which reached the highest wind speeds at landfall ever reliably recorded. The 2015 season produced Typhoon Kopu, Typhoon Mujige, and Typhoon Champi, which were among the most intense storms of their respective tracks. These precedents demonstrate that the Western Pacific can produce extraordinary seasons under the right conditions, and that the current season, however unusual its intensity distribution, is not necessarily unprecedented in every respect. The more important contextual question is not whether the current season's statistics exceed those of previous extraordinary seasons in every metric, but whether the conditions that are producing the current unusual distribution are themselves more persistent or more extreme than the conditions that produced previous extraordinary seasons. and whether the trajectory of those conditions suggests that future seasons will be more likely to show similar or greater intensity shifts. The answer that the science provides to this contextual question is cautiously affirmative. The conditions that are producing the current season's unusual intensity distribution include components that reflect natural variability and therefore will not persist indefinitely. Specifically, the ENSO and PDO states that will eventually return to less favorable phases. But the conditions also include the elevated oceanic baseline that reflects the longer-term greenhouse gas forcing, and that is not going to return to the lower levels of past decades. The natural variability components will eventually cycle back toward less favorable phases, and the intensity distribution will likely return toward the historical average. But the historical average is itself moving, as the elevated baseline continuously shifts the distribution of potential intensities upward, and the extraordinary seasons of the future will have a higher baseline from which their extraordinary anomalies are measured. The communities of the Western Pacific Rim that have been living through the current season are experiencing it not as an abstraction or as a data point in a scientific analysis, but as a series of actual storms making actual landfall and causing actual damage and displacement, and in some cases, actual casualties. The human cost of the current season is still being tallied as the season continues, with each successive storm adding to the cumulative total of lives disrupted and infrastructure damaged and livelihoods lost. The specific communities most affected by the current season's unusual intensity are those that have found themselves in the path of storms that were stronger at landfall than the historical frequency of landfalling storm intensities would have suggested was likely. Communities that had prepared for moderate typhoon landfalls based on the standard hazard assessments for their location found themselves facing major typhoon conditions. Communities that had prepared for major typhoon conditions found themselves facing super typhoon conditions. The gap between the prepared for intensity and the actual intensity is not the same in every case, because the specific intensity of each storm's landfall depends on the track and the timing and the specific conditions the storm encountered on its approach. But the pattern of the gap being in the direction of the actual storm being stronger than what the standard hazard assessment suggested, as the most likely scenario, has been consistent enough across the season to constitute a systemic pattern rather than a series of isolated events. The response of the disaster risk reduction community to this pattern has been to begin the process of examining whether the hazard assessments and the building standards and the evacuation protocols that are based on those assessments need to be revised in light of the current season's evidence that the historical intensity distribution may be shifting. This process is slow because it requires not just the acknowledgement that something unusual is happening, but the development of revised quantitative assessments that can serve as the basis for building code revisions and infrastructure investment decisions. The scientific evidence needed to support such revisions is accumulating, but the translation of scientific evidence into policy action involves institutional and political processes that operate on timescales longer than a single season's data can directly motivate. The tension between the speed at which the evidence is accumulating and the speed at which the policy response can be mobilized is one that is visible in every discussion the disaster risk reduction community is having about the current season. The evidence that something significant is happening is present. The specific magnitude of the change and its likely persistence into future seasons is less certain, because the attribution science has not yet fully disentangled the contributions of natural variability and long-term climate change to the current season's unusual statistics. And the institutional processes that would translate even a robust scientific assessment into revised building standards and preparedness protocols have their own inertia that the current season's data, however unusual, cannot by itself overcome. What the current season is producing that may be more immediately actionable than specific policy revisions is a sharpening of the scientific and policy community's awareness of the gap between the intensity distribution that current preparedness infrastructure is designed for and the intensity distribution that the Western Pacific may be moving toward. This awareness, if it motivates sustained investment in both the science needed to characterize the shift and the policy development needed to respond to it, could produce improvements in typhoon preparedness that reduce the casualties of future seasons, even if the specific regulatory changes take years to implement. The atmospheric scientist who showed the comparison chart at the Tuesday morning briefing has spent the months since then in the middle of a scientific investigation that the chart prompted, examining the current season's data in the context of the longer-term record to determine how unusual the season actually is and what the most honest assessment of its causes is. She has been careful in what she claims and what she does not, because the scientific credibility that allows researchers to influence policy depends on the accuracy of their assessments and the accuracy of an assessment of a phenomenon, as complex as the interannual variability of typhoon intensity is not served by overstatement. What she has found in the months of analysis following the briefing is a season that is genuinely unusual in the statistical sense that its intensity distribution falls outside the range of the 2 sigma confidence interval for the historical distribution, indicating that it represents a departure from the historical average that is unlikely to have occurred by chance. She has found that the departure is consistent with the combination of favorable natural variability factors that characterize the current season, but that the magnitude of the departure, particularly in the upper tail of the distribution where the most intense storms reside, is larger than the natural variability factors alone would be expected to produce. She has found that the residual anomaly, after accounting for the contributions of the favorable natural variability factors, is in the direction that the theoretical framework for greenhouse gas-driven intensity change predicts, which is consistent with but does not prove a contribution from the long-term climate change signal. These findings are, in the language of attribution science, described as consistent with the expected impact of climate change, rather than attributable to it with high confidence, a distinction that reflects the genuine uncertainty in the attribution of any specific season statistics to a long-term forcing rather than to natural variability. The distinction matters for scientific communication, but it does not resolve the practical question of how typhoon-prone societies should respond to a season that is showing the kind of intensity distribution shift that the theoretical framework has been predicting for years. The comparison chart that she showed at the Tuesday morning briefing is still on her screen, the side-by-side display of the climatological average, and the current season that prompted 8 seconds of silence and the question she asked twice. She still looks at it sometimes, at the systematic shift in the distribution that is visible across the full range of intensities, and thinks about what it means for the communities whose lives and livelihoods, and in some cases, physical survival, depend on the accuracy of the predictions that she and her colleagues produce about the Western Pacific storms. The question she asked twice was whether anyone had seen a comparison chart like this before. No one had. The question that follows from that answer is what comes next. It is the question that the science is working to address, and that the communities along the Western Pacific Rim are working to prepare for, in the intervals between the storms that are defining this season as one that the scientific community will be examining for years. The storms are still coming. The season is not finished. The ocean beneath the typhoon tracks is still warm, still deep in its warmth, still providing more energy than the models calibrated to cooler conditions fully anticipate. And the forecasters who are watching the satellite imagery and processing the model output and writing the forecast discussions that will guide the preparations of the communities in each storm's path are doing what meteorologists do in a season that is showing them something they have not seen before. They are paying careful attention. They are communicating honestly, and they are hoping that what they are seeing is the most unusual season in recent memory rather than a preview of what future seasons will look like. The data will tell them, eventually, which of those two things it is. The communities along the Western Pacific Rim are living through the answer in real time. The atmospheric scientist pulled up the comparison chart at the beginning of the Tuesday morning briefing and did not say anything for approximately 8 seconds. The people in the room, her colleagues from the Weather Research Division of a major Pacific meteorological agency, were accustomed to her opening briefings with data rather than with words. But 8 seconds of silence while she looked at her own chart was long enough to shift the quality of the attention in the room. When she finally spoke, she did not begin with the usual summary of the previous week's activity or with the overview of the current large-scale circulation pattern. She began by asking a question. She asked whether anyone in the room had seen a comparison chart like this before. The chart was a side-by-side display of 2 typhoon season timelines. The left panel showed the composite climatological average of Western Pacific typhoon activity for the current calendar period, derived from 6 decades of storm track and intensity data, showing the typical distribution of storm formations, the normal pattern of peak intensity events, the standard envelope of where and when the major typhoons of the Western Pacific Basin tend to occur during this period of the season. The right panel showed the current season. The number of storms in the current panel was not dramatically higher than the climatological average. The locations of formation were not dramatically different. What was different, and what the silence in the room was about, was the intensity distribution. The storms in the current season panel were, as a population, stronger than the storms in the climatological average panel. Not all of them, not dramatically in the case of each individual storm, but the distribution was shifted, systematically and coherently, toward higher intensities across the full range of the season's active systems. The storms that had been tropical depressions in the climatological average were tropical storms in the current season. The storms that had been moderate typhoons in the average were strong typhoons in the current season. The storms that had been strong typhoons in the average were super typhoons in the current season. The distribution was shifted, and the shift was visible across the full range, not in one anomalous event that could be attributed to unusual local conditions. She asked again whether anyone had seen a comparison chart like this before. One of her senior colleagues said that he had not seen a chart exactly like this, but that he had seen forecasts suggesting that something like this might eventually happen. Papers from the research community going back several years that had projected how the distribution of typhoon intensities would shift. As the western Pacific Ocean warmed and the conditions for extreme intensification became more prevalent, he said that the papers had been describing a gradual process that was expected to unfold over decades. He said that looking at the current season chart, he was starting to wonder whether gradual was the right word for what was happening. No one else in the room said anything for another few seconds. Then the briefing began in earnest, with the meteorological precision and the operational focus that the institution demanded, but with an undercurrent of something that was harder to name than concern, and that shaped the way everyone in the room approached the data for the rest of that day. The Western Pacific Typhoon Basin is the most active tropical cyclone basin on Earth. It generates more named storms, more typhoons, more major typhoons, and more super typhoons than any